Welcome to the tutorial video series for the Integrated Environmental Control Model, or IECM. These videos are designed to show you various aspects of the IECM to help you understand how it works and how you can use it in your modeling efforts. You can find more information, including additional videos and our user manual and detailed technical documentation, on our website at www.iecm-online.com. This video will introduce you to uncertainty and graphing in the Integrated Environmental Control Model, or IECM. In this video, you will learn how to add uncertainty to parameters, create a graph displaying those uncertainties, and export the graph. In this video, we use the term uncertainty somewhat loosely to include true uncertainty, where the value of a parameter simply is not known precisely, as well as variability, where a parameter can take on a range of known values, such as a range of power plant sizes that might be of interest. We assume that you are already familiar with the basic use of the IECM, including navigation, configuration, setting parameters, and getting results. If you are not familiar with these things, please watch our Getting Started video first. Let's get started. For this example, we'll create a new pulverized coal plant with the typical new plant configuration. We'll go to the overall plant performance parameters, and we'll put some uncertainty on the capacity factor to reflect the range of values that it might have in a particular study. One of the columns on a parameter screen is labeled UNC, or UNC, short for uncertainty. We bring up the uncertainty editor by clicking the button in the UNC column next to the value. Let's take a closer look at the uncertainty editor. The top of the window gives us a summary of important information about the parameter. We have the title in units, the minimum and maximum value, and the current value. This value does not include any uncertainty, and we refer to it as the deterministic value. Just under the summary, we have a line containing a drop-down menu for the uncertainty distribution, a checkbox to allow us to use nominal values, and a spin box to set the sample size. We'll get to the last two later. For right now, let's take a look at the distribution menu. Most of the distributions here are fairly standard, such as normal and uniform. Two that you may not be familiar with are half normal and neg half normal. These are the two halves of the normal distribution, as you can see from this picture. Half normal is the half above the mean. Neg half normal is the half below the mean. We also have a user-defined distribution, which allows you to provide your own samples. We'll choose the triangular distribution for this example. Shifting our attention to the bottom of the window, we find a brief description of the distribution we've chosen. For a triangular distribution, there is an increasing probability from the minimum value to the middle value, called the mode or most likely value, followed by a decreasing probability to the maximum value. Above the description is a list of requirements for our chosen distribution. In this case, minimum, mode, and maximum are required to be in ascending order. Also, the minimum is required to be less than the maximum. Looking toward the middle of the window, we see a pair of lines, the top one labeled normalized, and the bottom one labeled nominal. This is where we'll enter the values that define our distribution. But before we do that, we need to understand what normalized and nominal mean. Nominal values are the values that are actually used by the IECM. If you specify nominal values, they will be used as is. If you specify normalized values, those values will be multiplied by the deterministic value to obtain the nominal values that will be used by the IECM. Note that changes in the deterministic value, which may occur automatically if it is a calculated variable, will cause the nominal values to change in this case. Also note that this calculation will break down if the deterministic value is 0, and the results may not be as expected in cases where there is a unit conversion needed which is not a simple factor, such as the conversion between degrees Fahrenheit and degrees Celsius. You may find that the easiest solution is to specify nominal values in such cases. In the middle of the line just under the summary, there is a checkbox labeled Use Nominal Values. This allows us to choose whether we want to specify normalized or nominal values. The IECM will calculate whichever line you do not specify based on the current deterministic value. This calculation is for reference and will change if the deterministic value changes. For this example, we'll give the capacity factor a range of 60% to 85%, with our current deterministic value 75% being the most likely value. Since we're thinking in terms of an absolute range, it makes sense to specify nominal values for this distribution. So, we check the Use Nominal Values box, set the minimum to 60%, set the mode to 75%, and set the maximum to 85%. As I fill in these numbers, I press the Tab key to go to the next value and to ensure that the final number is processed. We've finished configuring our uncertainty, so we click OK to save it and return to the main window. Notice the question mark that has appeared in the Uncertainty button. This question mark indicates that the parameter has uncertainty. Before we go on, there is one other thing that you should be aware of. You may notice that some parameters have a box in the Calc column, which is checked to indicate that the parameter is being calculated by the model. If you have specified your distribution using normalized values, the deterministic value will be used in calculating the samples, and changes in the deterministic value may result in a distribution that is different from the one you thought you specified. This is only an issue if you specify normalized values. If you specify nominal values, they are used directly and are not affected by the deterministic value. If the calc box is checked and you plan to use normalized values, you should think about whether you want your distribution to shift if the deterministic value changes. If not, you may want to either uncheck the calc box before you add uncertainty or use nominal values. For this example, we're not going to change any other parameters, so the next thing we need to do is see how our uncertainty affects the results. There are two ways that we can do this. We can go to a specific result in the result screens, or we can use the uncertainty analysis tools to view any or all affected results. Let's start by going to the Overall Plant Cost Summary result screen and looking at the total revenue required, also known as the levelized cost of electricity. We can see the deterministic result here, 61.4, but that doesn't tell us anything about the effect of the uncertainty we put on the capacity factor. In order to see the uncertainty, we need to bring up a graph. We can do that on a result screen, either a table or a diagram, by right-clicking the number and selecting Display a Graph of this result. Now we have a graph of the cumulative distribution function, or CDF, of the cost. We find the mean in the legend, 62.62, and, looking at the graph, we see that the mean is at 50% cumulative probability, which is where it should be. The graph also shows us the 95% confidence interval, meaning that 95% of the time, the graph will be in that range. in this case between 57.64 and 69.25. Going back to the results screen, you probably noticed some other potentially useful commands in the right-click menu. There are a couple of options for copying the graph, which we'll look at later. And there are also a couple of options for using this result in the more extensive uncertainty analysis tools. Let's put this variable in the x-axis and go to Uncertainty in the Analysis Tools section. The first screen in this section, Configure Uncertainty, allows us to configure the sample size and sampling method. We can also select which plant components will be included in the uncertainty analysis. The default sampling method is median Latin hypercube sampling, or median LHS, which is an efficient method of choosing samples from an uncertainty distribution. We will stick with the default sampling method and uncertainty areas. You can find more information on the available options in our technical documentation if you're interested. Right now, we want to look at the sample size tool. This tool is also available in the uncertainty editor. We see that the default sample size is 50. This means that all calculations in the IECM are repeated 50 times, each time using a different sample from the uncertainty distributions. So, the graph we were looking at shows the results of 50 values of the calculated electricity cost with an uncertain capacity factor. If your graph looks a bit choppy, or if you need greater accuracy in your results, you'll want to increase the sample size. Let's set the sample size to 100 for this example. Let's move on to the next screen, View Parameters with Uncertainty. Clicking on the list, we see that there is one parameter as expected, the capacity factor. If I click Go to this screen, it will take me to the screen where I can edit this parameter, in this case, the Overall Plant Performance Parameter screen. Moving on to the View or Graph Samples screen, we have the option of browsing all parameters and results affected by the current uncertainty. This screen includes the samples, a small preview of the graph, and various options to copy the graph or the samples for use in another application, such as a spreadsheet. Looking at the Variable Selection tool, we see that the total revenue required is pre-selected as we requested. Clicking on a different variable puts that variable on the x-axis and updates the summary accordingly. There are also buttons to put the selected variable or the cumulative probability on the y-axis. Although you can choose the contents of the graph on this screen, if you already know which variables you're interested in, you may find it easier to select them from the right-click menu as we did earlier. Both the x and y-axis can be selected this way. Also, since this is a more general screen, the detailed graphs do not include statistics in the legend. Statistics are only shown when viewing or copying a graph from the right-click menu. Since we're interested in seeing the effect of increasing the sample size on the statistics, we'll go back to the results screen and view the CDF from there. Using a sample size of 100 instead of the default 50, we see that the curve looks a little smoother, and the values for the 95% confidence interval have widened slightly, reflecting the greater accuracy. It was 57.64 to 69.25. It is now 57.54 to 69.44. But increasing the sample size also increases the time it takes to generate a graph, since the model has to run many more iterations. Some more complicated models, such as oxyfuel, may take noticeably longer to run if you increase the sample size. So there's a trade-off between accuracy and turnaround time. Now that we have the number of samples we want, we're ready to save the graph. The basic procedure is to copy the graph in some form and paste it into another program. The obvious choice for saving individual samples would be a spreadsheet. The choice for an image is more diverse, depending on where you want to use it and whether you want to modify it at all before you use it. However, since it is possible to paste an image into a spreadsheet, we're going to do that to keep things simple. The right-click menu has two options: copy this result as text and copy this result as a graph. If I copy it as text and paste it into my spreadsheet, it looks like this. The statistics are included along with all the samples. The samples are ordered by sample number. If you wanted a more complicated graph than what the IECM provides, you could paste additional variables in the columns to the right, and the sample numbers would line up. You could then sort them on whichever column you prefer before creating your graph. Creating graphs in a spreadsheet is beyond the scope of this video. However, if you're not already familiar with the process, Google "how to graph in a spreadsheet" and you will find a variety of tutorials. Going back to the IECM, copy this result as a graph gives me an image of the graph which I can paste into something else, in this case my spreadsheet, where I've put it next to the text I pasted in earlier. Probably most of the time you're going to want to copy the individual samples, since it's unlikely that the IECM's graph is in the correct format for whatever document you're working on. To see the other options, let's use this result on the x-axis, and go to the View or Graph Samples screen in the Uncertainty Analysis tools. The buttons on the right give us a few different options. The Copy Samples button is similar to Copy this result as text in the right-click menu, but it has fewer statistics and includes the sample numbers. It looks like this. The Copy Graph Values button lists the coordinates of each point in the graph. This allows you to reproduce the graph without having to sort anything. The Copy Detailed Graph button is similar to Copy this result as a graph in the right-click menu. It copies the image that would be displayed if you clicked Show Detailed Graph. This concludes our introduction to uncertainty and graphing in the IECM. We hope that this video has been helpful. To learn more, we invite you to check out the other video tutorials and documentation on our website at www.iecm-online.com.